students. So here I am just going to introduce you about the most basic problem of celestial mechanics, that is a two-body problem. Actually in celestial mechanics, whenever we consider the motion of bodies, we consider our system as a system of two objects or a system of three objects. Like if we want to deploy a satellite over the Earth's orbit, then we consider that satellite as one object and Earth as the second object. So a system of two objects. Similarly, like we deployed that Aditya L1 over the Lagrange point, so there we consider a system of three objects, like Sun was one, Earth was one, and the satellite that we deployed, that was third body. The problem, as the name suggests, is nothing but a system of two bodies. So we always consider the motion of two bodies in two-body problem. So for example, say if we have some body with mass m1 at position r1 and body with mass m2 at position r2, so we can define a vector between r and r2 as r vector, where r vector is nothing but r2 vector minus r1 vector. So when we say that two-body problem, we are considered with the motion of this r vector as a whole, that is the motion of these two bodies as a whole. So that's what we'll be looking into. The forces acting between them used to be gravitational force, which is nothing but a central force. So central force always can be given in the form of function of radial vector acting in the radial direction. So please consider this force acting over this m2. So it will be nothing but force in this direction, that is attracted towards m1, and m1 will be attracted towards m2. So force acting over m2 is opposite into the direction of r vector. So minus of Fr r vector is the force for F mass m2. Similarly, force on mass m1 is nothing F of r, and here the force is in the same direction as r vector, Fr r vector. These are the forces acting on these bodies. Now we can simply replace them by the mass into acceleration. So m2 acceleration of this body. Similarly here m1 r1 double dot is Fr r vector, minus sign is there. So now differentiating this r vector r double with respect to time, we can get r2 vector minus r1 double dot vector. If we put the value of r1 double dot and r2 double dot from these equations, we can write here r2 double dot is nothing but Fr r vector by m2, and here minus Fr r vector by m1. So it's nothing but minus of Fr r vector 1 by m2 minus 1 by m1. Now if we bring this term over this side, it will come out to be m2 m1 divided by m1 plus m2 r double dot vector is nothing but minus of r vector. So here we can see that it is nothing but again a mass into acceleration is equal to force. So this term is known as reduced mass, and in two-body problem we always consider motion in terms of this reduced mass mu. Now some interesting properties of this two-body problem are that the angular momentum is conserved as well as the motion is a single plane. That we can prove from this equation itself. So as here we can see r double dot is equated with r cap. So the direction of r double dot is in direction of r cap. So whenever we find the cross product of r double dot with r cap, it will turn out to be 0. And this term can again be shown as d by dt of r cross r dot is equal to 0. So from here we get that d by dt of r cross this v is velocity, which is r dot, is nothing but 0, as r cross v is constant. This says that motion is in a single plane. Now if we multiply it by some mass m cross r cross v, so we can term it as L, angular momentum. This is again constant. So we come to the second property, that the angular momentum is constant.